Hello everyone, my name is Harshita Salvi and today let's discuss how to process stream data in big data. So, what is stream data? Stream data is data in motion. It is a continuous real-time flow of unbounded data. Unlike static batch data, stream data is dynamic and constantly generated. It is characterized by its sources, nature, and implication. Let's understand this one by one. So it is collected from sources such as IoT sensors, social media feeds, server logs, financial tickers, and mobile app interactions. For nature, the each data point is a small sequential record, and the data set is conceptually infinite, with events generated continuously. And this requires a shift from batch processing to stream processing. And the challenge lies in managing its velocity and ensuring chronological event order that is crucial for analysis. So let's understand why stream data processing matters. Here are two key reasons. The data deluge is real. So the global data creation will reach 181 zettabytes by 2025. That is a significant growth proportion and it is continuous high velocity data stream. And the second reason is instant data decision making. So we can gain real time insights from streaming data, and that is very crucial. Instant processing enables critical split second decisions across finance, healthcare, and e commerce. Processing data at creation unlocks unprecedented business value that helps in transforming reactive organizations into proactive, event driven enterprises. Let's see key characteristics of streaming data. Understanding streaming data's unique traits is essential for effective processing systems. So, the first key characteristic of streaming data is high velocity. The data in streaming data arrives rapidly, thousands and millions of events per second, and systems must ingest, process, and analyze immediately. Lagging diminishes real time value. The second key characteristic of streaming data is chronological significance. The event order is crucial. Events have event time, that is occurrence, and processing time, that is system observation. And correctly processing events, even out of order, is critical. The third key characteristic of streaming data is non homogeneous and imperfect. Streaming contains diverse formats, schema variations, late records, duplicates, and errors. So robust processors require mechanism for handling these imperfections such as data quality checks. So let's understand stream processing, that is a continuous computation model. So the core paradigm is here. The stream processing continuously processes the data record by record upon ingestion. Unlike batch processing, it's a perpetually active paradigm. So, here are the understanding. In memory operations, the data is processed in memory or in micro batches. For example, Spark streaming to minimize the latency. And the key operations involving here are as follows: filtering, enriching, aggregating, and event detection. So, the events are selected based on criteria. The records are augmented with external context such as geographic data. The sums, the average, and the counts are calculated over time windows, and the specific event patterns or sequences are identified in the last step. For example, failed logins. So the goal is minimal latency, that is the milliseconds, ensuring immediate and relevant insights. So here are two architectures of stream processing, that is lambda and kappa. Here are two primary architectural patterns that dominate the design of systems that handle both real time and historical needs. They are characterized, each one, by batch layer for accuracy and speed layer for real time for lambda and single stream for both and reprocess from log by kappa. Let's understand each architecture in detail. So the first architecture is lambda architecture. This is characterized by two distinct processing layers, speed layer and batch layer. So speed layer processes the data quickly with low latency, providing immediate but potentially approximate results. And the batch layer, it processes all the data, correcting and recalculating the final and accurate view. This layer ensures that the data completeness and correctness is ensured. Complexity. The complexity is high due to maintaining two separate code bases, one for batch and the other one for stream, and needing a mechanism to merge their outputs effectively. The second architecture is Kappa architecture. It was developed to simplify the Lambda approach and it uses a single unified stream processing pipeline. So it is characterized by unified layer, simplicity, and reliance. All the data is treated as a stream stored in an immutable append only log like Kappa Apache Kafka. The historical data processing is simply replaying the log from the beginning and significantly lower complexity because only one technology and one code base must be maintained, reducing development and maintenance overhead. It is highly dependent on a robust, highly scalable distributed messaging system, Kafka, for managing the data stream as the single source of truth. So, here are the popular streaming processing technologies. The stream processing ecosystem relies on powerful open source technologies for high throughput and fault tolerance. So here are four of them: Apache Kafka, Apache Flink, Apache Storm, and Spark Streaming. So each one of them is here. Apache Kafka. The standard for stream ingestion. Kafka is a high throughput, fault tolerant, and event driven platform that decouples data producers from consumers. Apache Flink, it is a true stream processor for stateful computations over unbounded data streams. Flink offers event time processing and efficient state management. Often it guarantees exactly one's semantics. Apache Storm, it is an earlier distributed real-time computation system that is focused on high-speed data processing and effective for simpler high-velocity tasks, but it is less focused on state management than Flink. Apache Spark Streaming, an extension of Apache Spark for near real-time processing using microbatching. The data streams are processed in small batches by Spark's engine, offering an easy transition for existing Spark users. So, to build a stream processing pipeline, here are the insights. A structured pipeline moves data from origin to actionable insights. So, the process is as follows: data ingestion. It collects the data from diverse sources, as we discussed before, like IoT, click streams, logs, into a durable message queue. For example, Kafka. The next process is real time processing. The core engine, like Flink or Storm, applies transformations like cleansing, standardization, enrichment, and windowed aggregation. And the last and final step is output and action. The processed results are delivered to an end system's live dashboards, automated alerts, or data lakes, or NoSQL databases for storage. Managing state is critical as processing relies on previous events. Example, running averages, session identification. So here are some real world stream processing use cases. Fraud detection. The stream processors analyze the transactions in real time and identifies the suspicious activities and blocks the fraudulent transactions instantly and significantly reduces the financial loss. IoT and predictive maintenance. So the real-time sensor data is analyzed to detect anomalies, triggering predictive maintenance alerts before critical equipment failure occurs. The last but not the least, e-commerce personalization. Click, search, and page view data is used to offer dynamic pricing, personalized recommendations, and tailored layouts, and often optimizing conversation. So, here are some best practices and future trends in stream data. Let's understand each one of them one by one. The first one is exactly one's semantics. Guarantee exactly one processing to prevent data manipulation, duplication, or loss. Essential for critical applications, Flink offers robust performance mechanism. Next is cloud and edge integration. Leverage cloud for scalable processing and edge for near source data preprocessing. This cuts latency and data transfer cost, particularly for IoT. AI powered stream analytics. It means to embed the ML model directly into the stream pipelines for real time scoring, anomaly detection, and automated actions without human intervention. And the last is lakehouse integration. Integrate stream outputs with lakehouse architectures to combine real time queries and historical ML workloads on unified data structures. So, overall, the goal is autonomous real time data intelligence. Thank you so much.